Well, so today we will be continuing with our discussions on the separated flow model. Till yesterday what we did, we deduced the two fluid model and then we combined them, we obtained the mixture momentum equation. We found that in that particular equation there was a numerator part, there was a denominator part, if you remember, and then naturally with analogy from your single phase compressible flows, which I would like to show you here, not this one, yeah. With the single phase compressible flows, if you remember in this particular case. So, we have also derived equation something of this sort, where we have a frictional pressure gradient, we have a gravitational pressure gradient, and we have a acceleration pressure gradient as well. Okay. And after that we found that since u is a variable in that particular case, so we had substituted u accordingly, and these all derivations we had got it. We found out that finally for compressible flows the pressure gradient also has a numerator term and a denominator term, just like it had for homogeneous flow, and now we have deduced the same thing for the two fluid model. Now, if you remember in the last class we had deduced the final expression. It was a huge expression. I would just like to write it down once more so that you can and I think it is there with you. So, you can just check up the denominator term which we have. This is the numerator term. This I have written down several times actually, plus g square dx dz 1 minus x whole square v 1 by 1 minus alpha whole square, sorry, minus x square. Just check up with the expression I have derived in the last class and let me know if I am just making some mistakes in writing it down. Plus 2x, this was already deduced, so you need not note it down anymore. So, this was the numerator part divided by 1 plus g square x square by alpha dv2 dp 1 minus x whole square by 1 minus alpha So, this was all we had already deduced it. Okay. So, now we find out that if we compare what we have in the transparency, we find that the denominator part is 1 plus d square dv dp. Here also we have 1 plus d square. Since there are two phases, we have 1 dv1 dp, 1 dv2 dp. Till this much we already had in the homogeneous flow model. Now, in this particular case, since alpha is also a variable, we have one term concerning alpha. Okay. And then if you look at the PPT, you will find that in this particular case we deduced that this 1 plus d square dv dp, this was nothing but 1 minus the Mach number corresponding to that particular fluid flow, is not it. So, therefore, this the denominator term, this was equal to 1 minus m a square. Now, if we start from the same analogy, then we are in a position to comment that this particular denominator, if you see with the denominator which we have deduced in the last class for the pressure drop equation or the pressure gradient expression that we had derived, this should also correspond to 1 minus the two phase Mach number for this particular fluid, is not it. This should also correspond, in other words, this should be equal to 1 minus MATP square. And from suitable modifications or simplifications of this particular expression which I have written down, we should be in a position to arrive at the condition of choking from the two fluid model, which is applicable for the separated flow situations, is not it. So, therefore, now what I am going to do, I am going to deduce the condition of choking from the two fluid model considering the mixture momentum equation. Okay. So, considering mixture momentum equation, condition of choking. What is the condition of choking by considering the mixture momentum equation? We find that the condition of choking in this particular case, naturally then this becomes 1 minus MATP square. This is the two-phase square, two-phase Mach number. This should be equal to the denominator which I had obtained in this particular case. Okay. So, therefore, this is equal to 1 plus g square x square by alpha dv2 dp plus 1 minus x whole square by 1 minus alpha dv1 dp plus del alpha del p at constant x 1 minus x whole square v1 by 1 minus alpha whole square minus x square v2 by alpha. Okay. So, therefore, now for the condition of choking 1 minus MATP square, this should be equal to 0 or in other words we get the condition of choking for a unit value of Mach number. That is what we had deduced for the single phase compressible flows, is not it? So, in this particular case also it is expected that the left hand side 1 minus MATP square, that should be equal to 0. In other words, this whole expression should be equal to 0 in order to obtain the condition of choking. So, equating the denominator to 0, we should be in a position to obtain the Mach number for, or rather from the two fluid model under the separated flow conditions. Right. Now, let us see what are the other sort of simplifications or modifications which we can do in this particular case, and from here consequently we can obtain an expression of the Mach number as obtained from the two fluid model. This is nothing but g square into x square by alpha dv2 dp plus 1 minus x whole square by 1 minus alpha dv1 dp plus del alpha del p at constant x 1 minus x whole square v1 by 1 minus alpha whole square minus x square v2 by alpha. Okay. So, therefore, the two phase Mach number should be the negative of this particular expression. Now, let us see whether we can express this in certain other simpler forms, so that it will be easy for us to assume. Again, we will start from the basic equations which we have already derived in chapter 4, which this one, sorry, this is alpha square. Okay. So, therefore, again we will start from the basic equations which we had already derived in our chapter 4, the equation of continuity and the basic definitions of W2 etc., etc. So, what were the basic equations that we derived? W1 equals to rho 1 U1 A1. Every day I write down these equations so that they get into your head and you do not forget how to start your derivations, or in other words this is nothing but this. Okay. So, from here we can get what is U1 equals to, it is nothing but W1 by rho 1 A into 1 minus alpha, or in other words this is nothing but W into 1 by minus x by rho 1 A into 1 minus alpha. Now, we know this W by A, this is nothing but G. So, therefore, this is G into 1 minus x by, see these things have to be there in your mind very thoroughly, otherwise it is going to be difficult. Okay. So, therefore, U1 equals to this. So, here we had something like 1 minus x whole square by 1 minus alpha square into V1, rho 1 means this becomes V1. So, therefore, from here you know what is this particular term, is not it? We can substitute it here and we can find it out that 1 minus x whole square by 1 minus alpha square, this is nothing but equal to rho 1 U1 square by G square. Fine. So we can, instead of this particular term, we can substitute this particular term here. Huh? Rho 1 square, sorry, yeah. Okay. So we can substitute this particular term. Okay. Similarly, just like we have written an expression for u1, u2 also we can write it down, it is just g x by rho 2 alpha, right. If we derive it for one, the other one becomes very easy. So, therefore, from here we have got 1 minus x whole square by 1 minus alpha square in this particular form, or in other words g square into 1 minus x whole square by 1 minus alpha square equals to rho 1 square u 1 square, correct. In the same way we would like to get x square by alpha square, it is nothing but rho 2 square u 2 square by g square, and similarly g square x square by alpha square equals to rho 2 square u 2 square. Okay. So, these things, so therefore, here g square into 1 minus x whole square, this particular term we can substitute, x square alpha by alpha square into g square, this particular term we can substitute, correct. The other thing is dv2 dp and dv1 dp, these things we had already derived. If you can tell me what is this dv1 dp and dv2 dp, any idea? We had already derived these things. dv dp equals to, what is the velocity of sound, say for medium 1 and medium 2, yeah. What is the basic definition of sound, you tell me? A for any particular fluid equals dp d rho, isn't it, or del p del rho under isentropic conditions. Since here we have very less amount of friction and very less amount of irreversibility, we can consider this to be an isentropic flow, fine. So, therefore, what is the thing that we knew? We knew that A equals to dp d rho, or in other word A square equals to this whole, sorry, very sorry, A square equals to dp d rho, or in other words 1 by A square equals to d rho dp del for constant isentropic conditions. Since I have already assumed that this is del of S and our flow is occurring under isentropic conditions, so therefore, I am removing that del part here, right, all of you, any doubts? So, or in other words this becomes equal to d dp of 1 by V, agreed, or in other words these derivations I had already done in the class previously, or in other words we can write it down as 1 by A square, this is equal to, sorry, this is equal to d dv of 1 by V into dv dp. So, therefore, we find dv or rather del v del p at constant S, which is in this particular case dv dp, this is minus V square by A square, yes or no. So, therefore, what we can do, whatever we have substituted here, this particular term, then the other one is this one, this particular thing, and then dv1 dp is minus v1, sorry, u1 square I think, isn't it, v1 square, sorry, v1 square by a1 square, and dv2 dp equals to minus v2 square by a2 square. So, these things. So, if we make all these substitutions into the denominator of the momentum balance equation which we had derived, then what do we arrive at? Just do it and tell me what do we get under that circumstances. Do it, just do it and then tell me what are the things that you are getting under those circumstances. Simply if you make the substitutions, we get the Mach number of the two phase flow. Just make the substitutions and you tell me what are the things that we are going to get. If we make the substitutions, in other words if I put minus MATP square, then in that case what are the things that I am going to get in this particular case? This becomes equal to, you just see whether you are getting these terms or not, minus u1 square by a1 square into 1 minus alpha plus del alpha del p at constant x rho 1 u1 square by rho 1, this is u1, plus this rho 1 means from V1 I have made it 1 by rho 1, okay, minus rho 2 U2 square by rho 2. If you make all the substitutions, if you substitute your x square by alpha, substitute dv2 dp, substitute 1 minus x whole square by 1 minus alpha, substitute dv1 dp, then substitute these terms substitution I have already told you. So, if all of these are substituted and then finally you arrive at the derivation which I have obtained in this particular case. So, therefore, this gives you the expression of Mach number for the two fluid as obtained from the two fluid model. This is equal to U2 square alpha by A2 square plus U1 square 1 minus alpha by A1 square plus del alpha del p at constant x rho 1 U1 square minus rho 2 U2 square. And what is the condition of choking? For condition of choking, this has to be equal to 1. Is this portion clear to all of you? Please perform these derivations once again so that the entire thing is clear to you. Now, can you tell me the basic thing under what assumption we have derived this particular condition of choking? Louder. Isentropic, see, let me tell you one thing. When you had derived Bernoulli's equation, what was the thing that we had assumed? Frictionless inviscid flow, which is nothing but isentropic flow. So, therefore, for fluid flow usually we assume it is isentropic, because usually we consider friction when there is no friction, and whatever irreversibility that is confined in a very narrow portion. So, usually we assume isentropic flow. But can you tell me that under what condition this particular equation has been derived? If you look at the basic in the equation, the expression of dp dz which we had derived in the last class, and I had written it down once more here, it might give you a hint on what was the basic assumption which we took to derive this particular expression. See, if you look at this expression, I had assumed that V1, V2, these two things, they vary with pressure, isn't it? And what else did I, and alpha it varies with pressure. Okay. So, alpha it varies with quality and pressure, and the specific volumes they vary with pressure. Let me tell you, for most of the cases this particular term will be disappearing off. Okay. So, you just keep in mind when you are given a derivation in your exam, this is just a generalized form I have written, then in that case depending upon the problem in question, you will be eliminating the basic terms from the very beginning, so that your assumption, or rather your expression or your derivation becomes simpler. Okay. So, therefore, we had just assumed these two things. We had assumed that alpha it varies with quality as well as pressure, very justified, and we had assumed that both the specific volumes or the densities, they are function of pressure. What else can vary with pressure which we have not considered here? Something else can also vary with pressure if you see this particular expression. See, the first thing, I cannot give you much time to think, that is the tragedy here. See, I have taken dx dz to be constant, or in other words, your x does not vary with pressure. When does it happen? It happens under ordinary circumstances in absence of flashing. So, in this particular case we have assumed that flashing does not occur. If you remember, for the homogeneous flow model also, what we did initially, we derived it for this particular condition only, and then we assume that if flashing occurs, then x will also be a function of enthalpy and pressure. For the present case that I have assumed x is a function of H only, or in other words x can be obtained from the enthalpy balance or the heat balance equation, is not it? But for flashing, x is a function both of enthalpy as well as pressure. So, therefore, the equation which I have derived in this particular case, this particular equation, it is applicable the condition of choking in absence of flashing. Now, when we have flashing, under that circumstance what happens? Under that circumstances, this dx dz, this has to be written down as a function of h and p, as we had done in the previous case, and therefore, in the denominator certain terms like del x del h at constant p or something, or sorry, del x del p at constant h, along with some associated terms will also come, and therefore, accordingly the condition of choking will be different in presence of flashing. So, that I am not deducing, that has been left as a home assignment for your case, okay, to deduce the condition of choking in absence of flashing. The other thing which I would like to tell you is that, see, in this particular expression we will have something like del alpha del p at constant x. That means, when the quality is constant, how alpha varies with pressure. Okay. Now, this particular differential, this is usually derived from correlations which are obtained at moderate values of pressure. Now, when we talk of moderate values of pressure gradient, this means when the frictional forces dominate the inertial terms, and when frictional forces dominate the inertial terms, then naturally alpha is not a very strong function of p. So, therefore, in that particular term, this equation is slightly misleading. Okay. Only under conditions where rho 1 u 1 square equals rho 2 u 2 square and this term is no longer exists, it is fine. But for other cases we find that this equation is slightly misleading, because the term del alpha del p at constant x, this is usually derived from a correlation which is obtained at moderate values of pressure gradient when the frictional forces dominate over the inertial terms. Okay. So, if we have to arrive at a much more accurate expression, what will we have to do? For a much more accurate expression, what we have to do? We have to go to the basic momentum equations. The basic momentum equations, what did we do? We first derived the basic momentum equation for phase 1. We derived the basic momentum equation for phase 2. If we just consider these two basic momentum equations, then there we would find that we would get one particular term like 1 minus u 1 square a 1 square. For phase 2 we would get 1 minus u 2 square by a 2 square. So, they would give us the condition of choking separately for phase 1 and separately for phase 2. Then if we combine these two momentum equations, there we find that some alpha term will come, and if we observe that alpha term, we find that the choking of phase 1 or the choking of phase 2 or the choking of both phase 1 and phase 2 does not guarantee compound choking of two phase flow. Why? Because alpha can adjust itself and prevent the condition of choking. So, therefore, now what we are going to do is, we are going to consider the two phases separately. We are going to write the momentum equation which we have already derived in the last class, and we will just take up the final expressions that we had got, and again we will make some simplifications. We will be deriving the conditions of choking of the individual phases, then we will combine the two equations and we will try to arrive at the condition of compound choking. Now, this is usually slightly, it involves quite a good number of mathematical computations, and the most importantly it again requires all the derivations or all the expressions which we had, all the nomenclatures which we had defined in chapter 4. Okay. So, let us start with that and let us actually arrive at the condition of choking for two fluid model from the two fluid analysis which we had started. Now, just to keep matters simple, I would like to prefer, or I would like to take that particular two fluid expression where we had considered the change of phase as well. This is just to keep matters simple. If there is no change of phase in the problem which you have to deal with, then simply you ignore the change of phase terms and you can proceed accordingly. Okay. So, therefore, let us derive the condition. So, this was the condition of choking in absence of flooding as derived from the mixture momentum equation. Okay. Just remember this. So, next what we would like to do is, we would like to derive the condition of choking considering two phases separately with change of phase. Okay. So, let us find out that what will be the condition of choking under this particular situation. This is going to be the almost the last of the complicated derivations which we have, okay, because this will involve a good amount of things. So, just try to follow it very well, the way I am trying to do, how I am going to substitute. The final results you will get in several textbooks, but the intermediate derivations will not be there. So, those derivations you can just, that is why I am going to go into the details of the derivations, so that you can follow them and you can understand how the final derivations have been arrived at. Okay. So, if you remember in the last to last class, we had derived the basic equations, okay, for the two fluid model. If you remember, the basic was rho 1 u1 del u1 del t, sorry, u1 delta u1, this was equal to b1 plus f1 minus delta p, isn't it? From there I will just recapitulate a few things so that you remember. This is rho 2 del u2 del t plus delta u2 equals to b2 plus f2 minus delta p. Okay. So, for one dimensional case, one dimensional steady state case, where we knew that b1 is nothing but minus rho 1 g sin theta, b2 was equals to minus rho 2 g sin theta, and we knew that f1 it comprised of f1 to fw1, or in other words, if I write it down, by 1 minus alpha. Why did this come about? Somebody had asked me this question. This was because this entire expression, this is written for unit volume of fluid 1. Okay, this is written for unit volume of fluid 2. So, therefore, this F1 it refers to the leftover forces per unit volume of fluid 1. Agreed? But usually it is difficult when the two phases are flowing. We can very well identify unit volume of the flow element, which will comprise of fluid 1 and fluid 2. It is very difficult for us to separate unit volume of fluid 1 or unit volume of fluid 2 and perform and do the necessary things. Okay. So, what we had done is, this entire expression was unit volume of fluid 1, this was unit volume of fluid 2. Now, for combining, what we did, that suppose something is for unit volume of fluid 1. Okay. Now, we have the entire, or rather we have unit volume of the two fluid mixture. Out of this, how much of fluid 1 is there? Alpha amount is fluid 1, 1 minus alpha amount is fluid 2. So, therefore, if the effective force per unit volume of fluid 1 is F1, then per unit volume of the total two phase mixture, what will it be? It will be, say, F1 by 1 minus alpha, isn't it? So, per unit volume of the two fluid mixture was taken as capital F1, okay, where this one was F1 by 1 minus alpha. Did you get my point? So, therefore, I will just cut it down. So, F1 into 1 minus alpha is the total leftover forces in fluid 1 per unit volume of the flow field. Clear to you? Same way, F2 into alpha equals to F2, right. And what is F1 equals to? F1 it comprised of F12 minus Fw1. If you remember the interaction between the wall and fluid 1, interaction between fluid 1 and fluid 2, and when there was a change of phase, what extra we had? For change of phase, we had the total force U2 minus U1 dx dz. G dx dz was the mass rate of evaporation into U2 minus U1, which was the velocity change which occurred due to mass transfer, or sorry, due to phase change. You remember those things we had done already? This was the mass rate of phase change, G dx dz. That into U2 minus U1 gives us the total force which is associated with phase change. Okay? And out of this total force, we had assumed that 1 minus eta of the total force goes to phase 1 and eta amount of the total force goes to phase 2. Remember those things? So, therefore, we find F1 equals to F12 minus Fw1 minus of 1 minus eta into G U2 minus U1. These are all U2 minus U1 dx dz. The same way we can write F2, this is equal to minus of F12 plus Fw2 minus, this was F1, minus eta G dx dz into U2 minus U1. So, these things we had already derived, right. So, now if you substitute this F1 and F2 in this particular expression and assuming steady state one dimensional flow analysis. So, for that particular case, what do we get? The final expressions we get are for one dimensional steady state flow, we get rho 1 u1 du1 dz, there is no delta here, minus dp dz minus rho 1 g sin theta plus f12 minus fw1 by 1 minus alpha minus 1 minus eta by 1 minus alpha 2 minus u1 g dx dz. The same way for this was for phase 1. Similarly, for phase 2 again we have rho 2 u2 du2 dz. This is again same thing, we can write it down, just the subscript 1 will be substituted by subscript 2 and we have to take into account the directions in which the forces are acting in each of the phases. u2 minus u1 g dx dz, this is for phase 2. So, these were the two equations which we had already derived. If you remember, these are the two equations which we had already derived in the last class. Okay. By considering the momentum balance equation for phase 1 and by considering the momentum balance equation for phase 2. Now, from here, in order to arrive at the conditions of choking, again we have to substitute u1s with something, etc., etc. Now, let us see how we go about for these particular substitutions. Now, let us take this term for example. So, let us take this particular term and let us take this particular term. Now, we can write it down as just see what I am doing, rho 2 u2 du2 dz. Can this be written as u2 d dz of rho 2 u2 minus u2 square d rho 2 dz? Why I am writing that you will understand shortly. This d rho 2 dz can again be substituted, etc. So, this we can write the rho 2 u2 du2 dz in this particular form, yes or no? Well, now what is this d rho 2 dz? Now, if you observe this particular term, this is nothing but, this term is nothing but d rho 2 dp into dp dz, yes or no? So, again we get a dp dz dependence on the on one particular side, okay, on the left hand or the right hand side, whatever the case may be. Agreed? And now what is d rho 2 dp again? Just now I had derived what is d rho 2 dp. This part is 1 by a2 square. So, therefore, this particular term it can be written down as, so this d rho 2 dz, can we write this particular term as 1 by a2 square dp dz? Can we do this? Yes, we can write it down in this particular form. I will be going a bit slow because this derivation is slightly little more complex. So, if I substitute these things, then in that case what do I get? Then if I substitute rho 2 du 2 dz with u2 d dz of rho 2 u2 minus u2 square by a2 square dp dz, I can very easily do that, isn't it? Now, doing that, what do I get? Doing that I get u2 d dz of rho 2 u2 minus this u2 square by a2 square is what? This particular term, this is ma2 square, right, Mach number of phase 2. Okay. So, this is nothing but ma2 square. Okay. So, this into dp dz, this is nothing but equal to minus dp dz into whatever the rest of the things that were written down, isn't it? So, this is nothing but equal to minus dp dz minus rho 2 g sin theta minus f12 plus fw2 by alpha minus eta by alpha and all those terms which are there. Fine. Now, I can bring both the dp dz terms on one side, the same thing which I have been doing for all the derivations. Okay. So, I can bring it on one particular side, and on doing so what do I get? I get my, just check up the signs which I am, maybe I might make some mistakes. So, just see whether I am writing it correctly or not. What I have done, I have taken this dp dz this side. So, I get minus dp dz 1 minus u2 square by a2 square, correct, and this is equal to what? I will bring all the other terms on the right hand side. So, I get this is equal to u2 d dz of rho 2 u2 plus rho 2 g sin theta, all the minuses here are going to get plus f12 plus fw2 by alpha plus eta by alpha u2 minus u1 g dx dz. Can I do this, yes or no? This I did for phase 2. Agreed? Similarly, I can just write down the same type of equation for phase 1. There is no need of deriving it separately. Just the same type of equation I can write it down for phase 1. Yes or no? Plus rho 1 g sin. Just take into account one thing, the signs are very important. Okay, because here it becomes minus f12, sorry, minus fw1 by 1 minus alpha. This you have to keep into account. Again plus 1 minus eta by 1 minus alpha u2 minus u1 g dx dz. Same thing I have written it down. This is for phase 2, this is for phase 1. Agreed? I can write down these two equations. So, from these two equations what do I get? I get that when is phase 2 choked, when u2 square equals to a2 square, we all of us know it, and we have derived it from this particular equation. Agreed? When is phase 1 choked, when u1 square equals to a1 square, this also all of us know. When is this two phase system getting choked? We cannot say u1 equals to a1 and u2 equals to a2 will guarantee the condition of compound choking, because there is good amount of alpha part also here. Moment there is some alpha part, this alpha is also a function of pressure. So, unless we can account for alpha being a function of pressure and bringing those things also on the right hand side, we cannot arrive at the condition of compound choking. Is it clear? So, therefore, remember one thing, choking of phase 1, choking of phase 2 does not give you any idea about choking of the two phase mixture. Why? Because the composition, the in situ composition of the two phase mixture is very important, and this particular the in situ composition, how it varies with the pressure gradient and other factors is also very important. Correct? Now, we have to go for that, we have to find out that how alpha varies, we have to substitute that, and then only probably we can get at two equations which we can combine and we can get the condition of compound choking. For that, what we have to do? Let us consider the equation of continuity. So, from equation of continuity, what do we get? I am deriving this whole thing, I have not prepared a transparency so that it becomes easier for you to follow the derivations, and if you do it along with me, when I am doing it, you will get some time because I am also writing down the things. So, probably you will get a little more thorough, this is the only reason, otherwise I could have prepared some transparencies and I could have shown it to you. Okay, means my course coverage could have been faster under that particular circumstances. Anyhow, so from equation of continuity, what do we know? We know W x equals to rho 2 u 2 a alpha. Agreed? Same thing, I will just write it down for phase 1 as well. So, this is for phase 2, similar things I will be writing for, I will be writing for phase 1 as well. So, W into 1 minus x equals to rho 1 u 1 a into 1 minus alpha. Agreed? Achha. Now, by logarithmic differentiation, this we have been doing quite a number of terms, and you have also done it, I believe, in your other subjects as well. So, by logarithmic differentiation, what do we get? For this particular case, we get 1 by x dx dz 1 by a dA dz. Why I am doing this? After write down the expression, it will be clear to you. Plus 1 by rho 2 u 2 d rho 2 u 2 dz. So, can you understand what I want to do? I want to substitute this rho 2 u 2 with things like say x a etc., alpha, so that I can find out all sorts of alpha dependencies in this particular equation, and I can substitute those alpha dependencies and then I can proceed. Well, I have to find out what are the terms which depend on alpha, isn't it? Then only I can bring the alpha dependencies to one side and find out the condition of choking. So, this is the thing which I can write it down, or in the other words I can write d dz of rho 2 u 2. Okay. This is nothing but, try to understand, into u 2, then I get this term u 2 d dz of rho 2 u 2. Okay. This whole term, if I want to substitute it in terms of say certain known parameters, then this whole term, what does it become? Just check up what I am writing, rho 2 u 2 square by x dx dz minus rho 2 u 2 square by a dA dz minus rho 2 u 2 square by alpha d alpha dz. Yes or no? Please follow the derivation carefully. So, I have simply substituted this, and accordingly I have brought the other things to the left hand side. I have got this particular equation. Agreed? Now, if I substitute this particular equation here for phase 2, then what do I get? If I substitute, just see, if you remember that equation, it was minus dp dz 1 minus u 2 square by a 2 square. Okay. This will be equal to rho 2 u 2 square by x dx dz. Agreed? I am just substituting that rho 2 u 2 by this particular term, this u 2 d dz of rho 2 u 2. I am just substituting this particular term. Okay. Minus rho 2 u 2 square by a dA dz minus rho 2 u2 square by alpha d alpha dz. Fine, I have substituted. Then the original terms which were there, rho 2 g sin theta plus f12 plus fw2 by alpha, whatever terms I had there itself. Fine. So, this again can be written down as, we have rho 2 u2 square everywhere. Okay. So, therefore, we can write it down as minus dp dz 1 by rho 2 u2 square 1 minus u2 square by a2 square. This is nothing but equal to 1 by x dx dz 1 by a dA dz 1 by alpha d alpha dz plus 1 by rho 2 u2 square. See whether I am doing it correctly or not, plus f12 plus fw2 by alpha plus eta by alpha u2 minus u1 g dx dz. See whether you are comfortable with the final expression that I have derived. Just see whether you are comfortable with the final expression which I have derived. Then once I have derived it for phase 2, similarly for phase 1 we can write down an identical equation. Okay. So, we have written down one equation for phase 2. In the same way, we can write down an identical equation of phase 1 by substituting u1 d dz of rho 1 u1 in the same way from the equation of continuity and performing the your logarithmic differentiation, and we can arrive at one particular expression for phase 1. So, we will be doing it in the next class, and then we will finally arrive at the condition of compound choking for the 2 phases under using the 2 fluid model. So, thank you very much.